All right, folks. So we are getting towards the end of the entire MOBISEC course. I'm getting a bit emotional. We have covered a lot of ground on Android security, and I think that the amount of information displayed in the slides, I think, is significant. And if you really manage to absorb all this information, you are really a step ahead. Of course, it's not the end of the journey; it's just the beginning. And many slides are just pointers to more information. But I think it's a lot of stuff that we've been covering. Before the end, I also want to touch a bit on iOS security because it offers a different perspective on a different design on a mobile operating system and the different trade-offs between security and usability and practicality. And it's also quite popular in terms of iOS is the operating system from Apple that runs on all the iPhones and so forth. So I thought it would be opportune to discuss this. One huge disclaimer: I am not an expert on iOS security. Okay, so what I actually did was I did the slides myself, but then for this last edition, since I'm going to be publishing the recordings online, I actually reached out to one guy that I met on Twitter, Ivan, who published very interesting reverse engineering, like an open source class on again reverse engineering on iOS apps. So he knows a thing or two about iOS security, and he was so kind to help me out and to check the slides and check for huge mistakes and so forth. Okay, so huge thanks to him. And so let's get it started. Again, it's going to be a very quick overview on iOS and iOS security, and I'm going to try to put the focus on provided the basics and also provided a comparison with Android to see what are, especially when things are different, so you can get exposed to a different design for some of the aspects. And Apple and iPhone was the first smartphone, so iOS somehow was born, let's say, before Android. I don't know if it's actually technically true, because Android was some kind of a company and then it was bought by Google, but for sure iOS, in terms of the operating system of the first smartphone, they were the leading ones. And as you will see, at the beginning, in terms of security, we were not as prepared as we are today. So there are many things that today we give for granted, but if you check how things were at iOS number one, you will be very surprised. Again, I'm going to try to cover these things and do my best in discussing this appropriately. We don't have time to dig into super low-level details, so just try to cover major differences and interesting points, and I'm going to point us at the end to where you can find more information. I want to have the disclaimer I just said by voice in writing. I'm not a super expert on iOS security. I believe I understand what I wrote in the slides, and I think all this stuff makes sense, and I try to read. I try to keep myself updated, but I'm for sure not an actual expert on iOS security. And I reached out to Ivan to check for big mistakes. He checked the writing. It could be that what I say is wrong, so there is no blame on him. It's all on me. Cool. So let's start from the apps. We are familiar with Android apps. Let's see what these iOS apps look like. They are written in Objective-C, which is a different language than Java and Kotlin or C and C++. Okay, and nowadays you can also write them in Swift, which again it's a language that Apple came up with, and it makes writing these apps much easier. We can think about Kotlin, Swift as the analogous of Kotlin for Android. So for a while, Android apps you could only write them in Java and C++, and then Google tried to step in and create a Kotlin. Things, language that is much easier to write for mobile apps. Swift, you can think about something similar. The code is compiled directly to assembly, which is in ARM. Okay, if it's an ARM-based processor. And the interesting thing is that, think about this, it's directly compiled to assembly. There is no bytecode. Okay, so in Android, if you write things in Java or Kotlin, this stuff is compiled to Java bytecode and then to W bytecode. And in the APK that you get, you can actually get the actual classes.dex, which contains the bytecode, which can be disassembled. Then we know many properties like types and so forth is it's decently easy to analyze. Instead, in this case, everything is compiled to assembly. And assembly, I hope you get this point at this point of the course, is actually much more difficult to understand and to disassemble. So there is no bytecode, and it's much more difficult to reverse engineer. Not impossible, but of course the bar is higher, especially for automated analysis systems. This stuff can get tricky, but it gets worse. So every method invocation is transformed to a call to this method, objc message send. And the second argument to this is method selector, and the method selector is a pointer to string. So in terms of W bytecode, what we have usually is invoke virtual, and then really the type, okay, the class type and the method we are invoking, and the types of the arguments and the type of the return value, okay. But here in this case, we just have a function called to this object message send, which is a function that you call directly in ARM assembly, and the argument is a method selector again, which is a string, okay. So if you check the code, you just see a bunch of calls to this object C message send, and the argument is not really a nicely, nice, representation of the type, but is a pointer to a string. And from the string, you can understand what this method is calling. So the string specifies with the method, and if you need to automate this, you may need to do backward data flow analysis and plus string analysis just to determine which method you are invoking. Of course, maybe in the basic case, the string that you're calling, it's easy to resolve it. Like maybe you have a pointer, you check the pointer, points to string, then that's it. But I just want to point out that it's a different level of difficulty with respect to W bytecode, where in Smalley you literally see invoke virtual to the actual function you are invoking. So the first big difference is that disassembling an app is not as trivial as with W bytecode. Okay. And that's something I didn't know, but Ivan pointed out to me that in Swift, the methods are actually mangled, so it's less bad. You have some kind of pointer to what these methods are pointing to. Okay, so in the general case, apps need to be published on the Apple Store before they can be stored on devices. And you may think, okay, whatever, but it's deeper than what we have in the Play Store. So on the Play Store, you can submit an app to the Play Store. If it's accepted, everybody else can install it and run it. But on Apple Store, that's the only way to run apps on your device. So if you find an app online, you cannot just take it and install it. Okay, on Android, by default, you cannot do it, but you can enable ADB, you can enable side loading of apps and so forth, and eventually you can push an APK. You just need to be signed, but again, it can be signed by any private, any certificate. Okay, it doesn't need to be signed by Apple or by Google. You can sign it yourself, and then you can install it. On Apple, you cannot do this. You cannot take an app from a website and install it on your iPhone. Okay, you cannot do this. So that's another big difference. Some details later on this topic. The other difference is that the app is shipped and installed encrypted. So once you get the app from the store, it's actually encrypted. You cannot see the content. Big difference from Android, where basically you can really write crawlers for Google Play Store. You download the APK. In the APK, you have everything. You have the manifest, classes.dex, and whatever else you want. In iOS, everything is encrypted. I think for the Play Store, I think if you download an app that is a paid app, I think it will be encrypted in the case as well, but that's not the case for normal application, while for iOS, everything is encrypted. This app is then decrypted at runtime when the app starts. So again, if you have enough permission on your phone, if you get through to it, if you get some kind of a way to understand what's going on and to hijack the control flow execution, you can basically run the app and then stop it just after the decryption, and then you can dump the content. But again, the bar is higher. Another thing I didn't know that Ivan pointed out to me is that only a portion of the binary is encrypted. and all the embedded files and resources are not. Okay, so it's not just one blob that is all encrypted, it's only a portion of the binary, and some files and resources are not encrypted. And apparently there are many developers that don't know about this, and they add secrets in configuration files thinking that these are encrypted, but they're actually not. Okay, another thing to keep in mind. Other thing is that iOS apps are developed with macOS Xcode IDE. Okay, and I tried to check for information how to compile apps for iOS without using Xcode. It's a pain. Okay, it's a pain. So just that you know. All right. So talking about security features. After all, it's a security class. Okay, one big thing is code signing. Again, this may ring a bell from the Android world, where basically every app needs to be signed. But remember, it just needs to be signed. It doesn't need to be signed by anybody in particular. Okay. For iOS, it's very different. Code signing, basically, one property is that only signed code will be executed by the kernel. Okay, so if you have a piece of code that is not signed, you cannot execute it. Okay. The key part here is that not every signature matters. It needs to be signed by Apple itself. If it's not signed by Apple itself, then this stuff does not run. Okay, again, huge difference with respect to Android. The thing is that only pages in memory that come from signed sources would be executed. Okay, so you cannot just allocate another thing and then put some code there and start to execute it. Okay, because the content of this memory page would not be signed. So again, the enforcement of this signing goes beyond the okay, is this app signed or not? It goes also touching on the at the memory page granularity, let's say. Okay. Apps cannot change their behavior and update themselves. It's technically also very difficult given these constraints. I think on Android policy, I think the recent Android policy is something similar. Basically, you're not supposed to use dynamic code loading to update yourself. You're supposed to use the Play Store technology, let's say, A/B testing and things like this. I think that is a policy thing, but it's actually quite easy to embed some kind of a dynamic code loading functionality in Android. But iOS, given these constraints that if it's not signed by them and you cannot really create a memory page, put some random comment from the internet and then run it because it's not signed, then this stuff gets tricky. This means also that apps cannot just download and execute arbitrary code. Okay, it just doesn't work because the content that is executed needs to be signed by Apple. So in a way, Apple, keeps the keys and to say what kind of code can be run on your device, and somehow the code is signed by Apple when Apple approves the app to the Apple Store. So, and that's why the only way to run code, the only way, quote, quote. So there are many asterisks and disclaimers. So check until the end of the slides. The reasonable or the expected way to get something signed by Apple is to submit to the Apple Store and to get it approved. Okay, that's the path. Okay, if you don't do this, then there are some exceptions, but if you don't do this, your app is not signed, which means that you cannot run it. Okay. And again, it's a huge difference with Android, where basically I can write my own app. I don't need to ask Google for signatures or anything, and I can just take this app and run it on my phone, even if it's not rooted. Okay. In Apple, you cannot do this. All right. So as I mentioned, there are some exceptions. These constraints will be huge if applied very strictly. So there are some exceptions, but as you will see, these exceptions are not like everybody does everything. Okay. So they're still quite constraining, much more constraining than what you have on Android. So the fact that Apple needs to sign everything is very constraining. There are exceptions. Let's see what they are. So one big umbrella of exceptions is about enterprise and universities. Enterprise and universities, they want to deploy their own apps. And I wrote in the past that they don't want to have Apple in the loop, which is technically not true because there is a way for these enterprise universities to not being super relying on Apple, but Apple is still in the loop. So the way it works is that enterprise or universities can register for an enterprise account, and then Apple provides the certificates signed by Apple to sign the enterprise apps, okay? After you get the certificates, then you basically don't have Apple in the loop. But of course, to get this enterprise account, you need to have Apple in the loop, okay? So that's just a clarification on this, why Apple is in the loop. Apple is in the loop, but not at the later stage, let's say. And then basically you have these ad hoc modified devices that can provision the code that they want, okay? I also wrote in the past that developers also a way to bypass code signing. Again, that's not technically true, because there is still code signing, but it's just that Apple provides some kind of a certificate that allows a developer to self-sign stuff so that they can try things out. So the way it works is that developers are going to get a developer certificate that lasts only 7 days. And with this, they can sign apps and test them on their own phone, okay? Yeah, some details more on this later. Cool. All right, other exceptions that may, if you take this code signing very, very strictly, some of the applications may not run properly, including browsers. So let's try to dig a bit deeper on how they chose this security vs usability or practicality trade-off. So code signing in theory affects all code and libraries, all of them, okay? But browsers need to do JIT, JavaScript. So for those of you who are not familiar with JIT, JIT stands for just-in-time compilation. And the idea is that you visit a web page. Web page is constituted by HTML, CSS, but also JavaScript. What is JavaScript? Well, it's a language that it is interpreted by your browser and it's executed in your browser, okay? And the way that it works from the technical standpoint is that they take this JavaScript code and then they JIT it. What does it mean is that they take this code, JavaScript, and they compile it on your browser. This is compiled to machine code, binary code run by an ARM processor, for example, and is actually executed. And JavaScript is served from web pages, and Apple cannot preemptively sign them all. So now you are in a situation where a browser, to actually work properly, will need to take some information from a website, JavaScript code, compile it and run it. But if you take this code signing rules very, very strictly, you cannot do this, because Apple did not sign the machine code coming from the compilation of JavaScript. So there are exceptions, and for example, mobile Safari or browsers can create a write and executable area plus JITting, okay? So to prevent abuse, you can only create one of such area, and this is only done to browsers, okay? So mobile Safari is one, and so mobile Safari can have one area of memory where it can basically write assembly and actually execute it, okay? So that's how they, it's a trade-off, of course, because potentially it could be abused, and this exception goes against the strict application of only signed code could run, but it was mandatory, otherwise these browsers would not work. All right, other security things, data execution prevention. So you have code and data sections in applications. Code sections are not writable, data sections are not executable. That's something similar that you have on in Linux, okay? When again, usually you have code and then the code section is not, or the code segment is not writable, you can just execute it. The data section usually is not executable. So you can write it, but you cannot really execute. And there's a protection so that an attacker cannot just write some executable bytes somewhere and then just execute them, as they would do in the past with just shellcode and so forth. It's more complicated. So in terms of protection, there is nothing particularly new. At least I guess there is nothing particularly new. There is same protection in Linux. Conceptually, the bypass is to use code reuse or return-oriented programming to create first a write executable memory, and then you basically load the stage 2 in this writable executable memory. But in iOS, it's trickier because you cannot create a writable and executable memory. So the entire payload needs to be executed with drop in that case, okay? Or executed, needs to be implemented in drop. Again, I'm going a bit fast on this because these are topics explored in many other classes, CSEC at Eurocom and so forth. So cool. All right. Another layer of security is the Apple Store app reviews, which is something we already touched on the Play Store part. Again, this somehow, it's bypassable. Yes, you can maybe sneak in something malicious in the Apple Store, but it's yet another layer of security. So, as it happens on the Play Store, on iOS, developers develop iOS apps, and then they need to submit them to the store for approval, okay? The review process seems, I don't have details on how it actually works, behind the hood, but to my understanding, it seems more, more thorough with respect to Google. And I just have anecdotal evidence. I have friends whose app got rejected because the UI was not nice enough. While in the past, for some previous research, I was able to submit some random apps to the Play Store, and they were accepted. Nobody was actually checking them. And this friend of mine, again, he got rejected literally because the UI was not nice enough, which it hints to the fact that there is some human involved in the process. That's not some task that an automatic system can easily perform, unless maybe the UI of this friend of mine was so horrible that even a machine could understand that it was very bad. I don't know. Again, these are just anecdotal evidence. I don't have any concrete information on the topic, and this evidence comes from maybe 2 years ago, and things are getting better and better. If Apple then approves it, then the app code is signed, and it can be executed on Apple devices. Okay, as I mentioned before. Cool. Now, this code signing, is it really impossible to bypass? Well, kinda no. Like, is there any way? So what does it mean bypass? First of all, well, with bypass we mean a situation where a developer can execute additional code after the approval. Okay, so in a way the developer is able to execute code that is not technically signed by Apple. People have found bugs in the code signature verification process. So as any piece of software, there are always bugs, and people found bugs also in the piece of code that should verify if a piece of code is signed or not. But is there something deeper? And the answer appears to be yes. That's a very interesting research paper to some of my old collaborators at Georgia Tech, where basically they found out a simple way, but it's simple, but it's quite interesting, a way to bypass the system. And the idea is that you write your own app, and you write the app in a way that it contains a memory corruption vulnerability intentionally. Okay, you put a memory corruption bug there in a hidden way. Okay, and you submit it, and the hope is that Apple doesn't find it. And, it's a fair assumption because finding these bugs is very difficult in benign apps. If the model here is that you have an attacker that is submitting an app with an intentional memory corruption bug, this can be as obfuscated as the attacker wants. Okay, so in general, I think it would be very difficult for Apple to find automatically all these bugs. The idea is that after it's approved, then once the app is run, you somehow exploit this vulnerability to gain arbitrary code execution. So the idea is that in this app you submit, you put some memory bug, but you also put a lot of material to be useful for return-oriented programming gadgets. And after this stuff gets approved, then maybe you can send an exploit that mixes up all the gadgets you have and somehow execute the arbitrary code that the attacker wanted. Okay, so it was a beautiful trick, and to the best of my understanding, is still an open problem. Okay, nothing much that Apple can do. With that being said, honestly, I'm not aware of big known cases of abuse of this. So it's more like a technical trick and not something that I've seen abused a lot. Okay, so more details about how the system works. One aspect to cover is the provisioning system. individual developers need to test their apps. Okay, so, and again, if you take this code signature strictly, then it's a nightmare, because you cannot just hope that Apple you submit the app to Apple, it's approved, and then you test it. You need to be able to test it before submitting it. So there are some steps for the developer. First of all is to create a developer account with Apple and pay an annual fee. Then you generate some crypto keys. Then you generate a provision file and specify which device she wants to use. Okay. So basically, you need to somehow identify the device you want to use, the test device, and then tell Apple. And then entitlements, which are basically special capabilities that are required by apps. Okay. So there are a bunch of entitlements that you can ask, and this should be part of your request. And after you have this, basically now you can run the app on the device you selected. Okay, so that's the way in which Apple somehow still enforces the code signature verification, and somehow still allows developers to test their own apps. Okay, cool. Other things. Modern versions of Xcode and iOS allow developers to install apps outside the Apple Store, but only if the source code is available. So that's another thing to keep in mind. But all these constraints that I gave you so far is one of the main reasons, many reasons on why doing research on iOS is a pain. There are, of course, extremely successful researchers working on iOS. I'm just saying that the bar to play with things on iOS is more complicated than on Android. Okay, and the ones I provided so far are just some of the problems, and I'm going to have other problems to discuss later on in this presentation. Okay, so other security mechanisms on iOS. Well, Apple toolchain supports classic protection mechanisms, SLR, stack canaries, and so forth. And again, these are covered in traditional security classes, so I'm not gonna go deeper on this. There is a concept of app sandbox, as we have on Android. So we have the concept of privilege separation. So apps have users and groups. They run in different processes with different users. This is very similar to what we have on Android. But the sandbox is actually stricter than Android's. For example, apps can only read and write their own files. Okay, on Android, if you ask for the SD card permission, you can get access to other files. Another thing is that apps can read external files, but only via user interaction and input. Okay, so for example, on Android, you have apps like WhatsApp, and you may want to be able to share a picture. So you can click on a button to share picture, and WhatsApp is going to access the SD card where the pictures are, show you something, and you can pick what picture you want to send, and then you send it off. Okay. On iOS, you still have the opportunity to do something like this, but it's not the app itself that has direct access to the SD card. It's basically the way it works is that the app needs to say, hey, I would like to ask the user which file to select. Okay. And then basically some pop-up from the system, not from the app, is shown to the user, and then the user can interact with it and say, okay, I want to share this picture and this picture. Okay. And then these pictures are shared. This is a huge difference, because in the first case for Android, once an application has this SD card permission, you can read files and send them off the internet. You can do whatever you want. While in this case, this access to external files is still possible, but it is mediated by the system. So, and the system makes sure that the app can get files only after a user interaction. Okay, so it's a huge difference. Example, to transfer a file from an app to another one, the app needs to show a UI picker. That's the interface that I discussed before. And again, the user needs to be involved. She cannot be left outside the loop by design. And it's the bar for abuse is much higher with respect to Android. All right, other topics, permissions. So in the past, all apps run in the same type of sandbox. Okay, and the idea was that if it's okay for a third-party app to have access to capability or permission X, then all third-party apps would have access to it. it's completely different than what we have now. So this may appear a bit strange, but that's how we started. Okay, so you have system apps, you have third-party apps, and then they thought, okay, third-party apps should have access to X, Y, Z, and if that was the agreement, then every third-party app would have access to X, Y, Z. Okay, there was no permission problem, there was nothing like this. Again, there was no permission system, and apps were able to access address book, GPS info, and so forth. But note that in early versions of iOS, only system apps could be installed. So now we are so used to the idea that there is a Play Store or there is an Apple Store, and you go and you install whatever app you like. But in the past, it was not like this. You buy the phone, there are system apps, and that's it. Okay. So the threat of abuse from third-party apps was much, much less. Okay. Again, there was no Apple Store. In modern versions, it's different. So there is a permission system like Android. Actually, it's a permission system like the new Android runtime permission. Okay. So in the past, as you may remember, Android was following a all or nothing approach. Once you install the app, it will show you the full list of permission, and then you need to say accept, and that's it. While iOS, even at that point, it was showing up a prompt like, hey, this app is asking for a location. Do you want to get access to it? So there was some kind of a runtime permission, and some of the users had more context to say yes or no and so forth. Then I guess Android folks understood that this is a better way, and somehow the new version of Android migrated to this runtime permission, and that's the system that you are very familiar with. Okay, asking for location, SD card, and so forth. Permission system, so is similar, but third-party apps cannot ask for the crazy permissions we've seen on Android, like draw on top, this system or window, accessibility service, all these UI security attacks that I've shown before, to the best of my knowledge, are not applicable to iOS, because third-party apps really cannot get access to this draw on top permission and so forth. Okay, so that's an entire class of attacks that is not relevant for this iOS. I guess they did it so that apps cannot be very intrusive. They cannot pop up ads somewhere, and my feeling is that Google somehow regrets that there was this drawn top permission out there that now is abused, but it's also used by many legitimate apps, and it's very difficult to just remove it. But it is what it is. Okay, so another interesting aspect about iOS, which does not have an analogous counterpart in Android, is public and private APIs. So public APIs are basically APIs described in the Apple documentation as it's normal, okay? And the apps can use them without problems. Private APIs are very interesting. These are, there are a number of APIs that are private. What does it mean? They're not discussed in the documentation, but that's the only distinction between public and private. From the technical perspective, these private APIs are available within the memory space of every app. So imagine that you have a library, and this library is a bunch of functions. Some of them are documented. These are the public APIs. Some of them are not documented. These are the private APIs. So from the technical standpoint, these private APIs are just hidden. But from the technical standpoint, an app can just invoke them. Okay, so it's somehow based on trust. It's a kind of an interesting design. Again, the problem is that there is of course potential for abuse. There are many ways to discover them. Once you know that there is a function there is a way to enumerate them and discover them in runtime and so forth. It's of course against the term of service, but if you don't get caught, you can get away with it. Again, Apple's term of services says you should not do this, and if they find you, they would reject you. But apps can technically do so, so it's very likely that somebody does so, especially because, as we mentioned before, analyzing these iOS apps is not simple. At least it's not as simple as the Android apps. In the Android world, if you have some kind of Java APIs exposed, under the assumption that you have only Java code, it's very easy to disassemble it, do a scan of the APIs invoked, and then just say, oh, you're invoking a private API, you shouldn't do this, I ban you. But of course, you can also bypass that, because if you move to native code, then good luck analyzing it. But even in the basic case on iOS, it's very difficult to fully analyze an application. Okay, so the bar for detection is higher. And there was a very interesting paper a while ago that somehow wrote an entire analysis system, try to understand whether iOS apps are actually using these private APIs. And this guy found that yes, 7% of the apps at that point, I don't remember I think it was 2016, 2017. So 7% of apps at that point were actually using private APIs. And I remember I was at this presentation, and I could feel the pain of these researchers trying to make this stuff work. Very interesting work, but the interesting part was that just to make the tool set working was super complicated because of all the limitations of all of the let's say problems and technical challenges that you need to overcome to have a successful iOS app analyzer. All right, so more notes on additional hardening from the iOS operating system. There is no shell in iOS. Okay, we have one in Android. There is no shell in iOS. So you either run stuff in the context of the exploited device, or you need to bring all the code you need with you. Okay, so once you exploit something, it's not that you get a shell and then you do stuff. You need to bring everything with you. iOS is based on BSD, but some calls are disabled. For example, system fork exec are disabled. You cannot invoke them. So an app cannot start a new app or launch a binary tool to process data. Okay, you just cannot do this. Well, of course, you can do this on Android. You can do this on Android, depends, right? Because it depends on the Linux policies and so forth. But for example, on Android apps, even if you are a third-party untrusted app, you can create a new process. In Apple, you cannot. Okay, so again, different trade-offs. In iOS, an app, of course, can start a new thread. Otherwise, you cannot pretend that everybody does everything a single thread. But again, you start a new thread, but it's all belonging to the same main application. Additional hardening, again, we have secure boot. This is similar to Android's. We have data encryption, again, similar to Android. And the idea is that you have a UID key. This is embedded in the hardware, but is not accessible via software. We can call this a device key, okay? And that's different for every device. Then there is a user-provided passcode, let's say, that somehow unlocks the device, and together with the UID key, it builds the passcode key, okay? And with these things, you can have, on iOS, you have 4 protection classes for files. So basically, once you have a file, you can tell the system which protection class you want this file to belong to. The first protection class is complete. It means that the file is protected and can be accessed only when the device is unlocked. So if the device is actually unlocked, you can access it. If the device is locked, no matter what, no matter if you already booted, no matter if you authenticated once, no matter for anything, you cannot access the file, okay? Complete as less open. Basically, the file can be open only when unlocked, but then it's accessible. So if you start the phone, if you unlock it, and you try to open the file, you can do this. But if you try to open the file while the phone is locked, then you cannot do this. And the difference with the previous part is that once you open the file, then it's fine. Then you can use the file. You can you can access the file, even if even if you lock the phone. So the important part is that you can open the file once it's unlocked. If you do this, then even if you lock the device, the file is still accessible. Another protection level is protection until first user out. So basically, the file is protected until the device boot and you unlock for the first time. So if you reboot the phone, everything is still locked. If you lock the first time, then the file can be accessed, no matter where the device is locked or not. The last protection is no protection. So the file is always available, okay? Cool, and depending on the use case you have, maybe you have a clock application that wants to store alarms. Maybe you would say, okay, the file containing which alarms are set or not, maybe they fall to no protection, so that if during the night the phone resets itself and reboots, then this file is still accessible by the system, okay? So it's up to the developer figuring out which protection is better for her. All right, more survey on these techniques of hardening. Kernel integrity protection. So after the iOS kernel completes initialization, basically the memory controller denies writes to the protected physical memory region. Okay, so you cannot just modify it. Other things, you have Touch ID and Face ID. These are similar things that we've seen with the fingerprint API and some kind of face recognition and biometric prompt API of Android. For the Touch ID, there is nothing special with respect. I mean, it's complex technology, of course, but there is nothing special with respect to what you can expect from a Touch ID technology. The Face ID is some kind of a high-tech stuff where basically they project an invisible grid of dots, and they project to your face and they build a 3D model, and from this 3D model they say, okay, that's you or not. Okay, so that's the next level. It's not that they take a video or a picture and then they say you look like the owner, but they actually get a 3D model, and it seems this stuff is actually resisting. There was a claim at that point from a company that it has been hacked. For completeness, I listed here. There is a link to the news article, but news is quite old, and honestly, I haven't seen much stuff as a follow-up. So it could be that it was an overclaim. It could be they broke one specific phone, but not the system. I don't know what's going on. But again, the current state is that, to the best of my knowledge, this is not profoundly broken system, and you know, you can somehow rely on this. Cool. All right, moving on. We have another aspect that is a secure enclave. Again, new name, but we have seen this technology in the past. Secure enclave is a separate high security processor. Does this remind about something? Well, it's the analogous of ARM Trustzone. Okay, Trustzone somehow was a technology that allows to have as a separate mode of the processor that runs in a secure way, and so some memory parts or some peripherals are only accessible if you are in Trustzone mode, otherwise no, or in secure mode, otherwise no. Same stuff with the secure enclave. Okay, yeah, so secure enclave checks that its own software is signed by Apple before booting. Again, similar thing that is enforced by the chain of trust and the secure boot process in Android, where you have, I think, I don't remember which step, but maybe a boot that cannot be modified, or a boot that can be modified but is integrity is checked by the previous part, and then this guy is actually the one that checks the integrity of the code that would run in secure enclave, and if the integrity is met, then it runs, otherwise no. And this check is not possible to disable the check, not even on Android phones where you can unlock the bootloader. There is no such thing in Android, in iOS. So this stuff is considered trusted. And many security related APIs rely on it. For example, encryption stuff, Touch ID, Face ID, Apple Pay, and guess what? These are some of the APIs that also Android is relying on Trustzone to implement properly, such as, you know, the fingerprint API, the biometric prompt, the, you know, Google Pay stuff, or storing key store material for again, encryption stuff and so forth. Okay, cool. Another thing, there is a new technology called pointer authentication codes, short PAC. So basically, it's a you know, think about stuck canaries. Okay, stuck cookies. It's some kind of a protection system that doesn't make, you know, maybe there is a bug, but it makes it slightly more makes it more difficult to exploit, because maybe detects that a buffer has been overflowed. PAC is basically another of these techniques, but you know, it's much more powerful. Basically, you have pointers, so code pointers or data pointers, and you can protect these pointers with PAC. And somehow the way it works is that now you have a pointer. This pointer doesn't only encode, you know, doesn't only point to a memory area, but it also contains some kind of crypto or authentication tag. And the code itself, before using this pointer, is going to check that the tag, the crypto part, is actually correct, or its integrity is verified. Okay, and the idea is that an attacker cannot arbitrarily alter a pointer to make it point somewhere else, even if she has full write capabilities. So on Linux, or, you know, in Android systems, if you have full write capabilities and you can selectively say, hey, this pointer, you should point somewhere else, then chances are that once the code get there, you're going to jump there. Maybe then getting a shell out of it and so forth, maybe it's tricky, but if you control a pointer, you can actually jump somewhere. Here, even if you have full write capabilities, you cannot do this, because sure, you can override this pointer, but when the system works, this pack works, you cannot predict what kind of tag you should put if you change this value. So you can change the value, but if you change the value, also this crypto tag should change, but you don't know how to set it because the crypto material is stored somewhere else. And somehow you get the idea, right? Even if you change this, the system is going to detect that the pointer is not valid, and the exploitation is more difficult. So the idea is to mitigate memory corruption vulnerabilities, making them more difficult to exploit. Per se does not remove the presence of a vulnerability itself. Again, it's not impossible to bypass it, and some techniques are known. This was posted last year. Again, that's one example. But again, of course, it requires much more advanced techniques. I'm just saying it's more difficult, but it's not that it solved the entire vulnerability problem. There are still tricks to get around it. Cool. Again, about this specific technique, there are more information about Qualcomm, which is the company that actually took care of implementing this. So it was an interesting read. So check it out if you want to know more and exactly how these tags work, where the crypto thread model, where the crypto material is stored, and so forth. All right. So again, as you see, the style of the slides is basically like a huge list of interesting aspects to discuss with Android. We distributed this over many classes, so it was possible to organize each class by a theme. Here I have one shot to cover everything I can about iOS. So sorry that maybe these slides go a lot of reverse engineering, security mechanisms, and now this jailbreak, whatever it is. But it is what it is. Cool. So about the jailbreak. So iOS devices are very closed down, okay? And in a sense that you cannot install your own apps, blah, 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 okay? And again, even if you can install your own app by having some kind of a dev test certificate and so forth, you have a third-party app and it's very constrained. You cannot have drone top, it's not that you have a system app, okay? And somehow users want to do more stuff with their devices. So this leads to the idea of, hey, I want to jailbreak my device. What does it mean? Well, in the iOS community, jailbreak is a term that identifies the process of getting root on these devices so that you can customize it and so forth, okay? So why one would like to jailbreak? One is to disable some security checks, install arbitrary apps, even third-party closed source apps that are not approved by Apple. You may want to get root access just for the sake of getting root access. You may want to load arbitrary customizations that are not possible if you just install a third-party app. You may need to modify the actual system, okay? So you may want to have custom UI, custom kernel, and so forth. Even if you can install arbitrary apps, you cannot do this unless you jailbreak it and you get root, okay? There is Cydia. Cydia basically is a package manager for iOS mobile apps, and this Cydia is actually used on jailbroken iPhones to install third-party apps. So the idea is that once you jailbreak your iPhone or your iPad, then you can install Cydia. Cydia is like a package manager, like some kind of a store for third-party apps that are not signed by Apple, but that you may want to install on your system. And the developers of Cydia also created the Cydia Substrate, which is a framework to modify iOS with extensions, okay? Again, there is a huge community about jailbreak. The first jailbreak was for iPhone 1 in 2007. Then there were several jailbreaks that followed this one. One of the famous ones is jailbreakme.com, which was a remote jailbreak in 2011. And this was also called with this jailbreakme 3.0. And the idea is that you would be able to jailbreak your device by just visiting a URL. So you would basically go to a URL and then bam, the exploit is run and your device is jailbroken. So it was actually very, very powerful. And it was pretty cool because people were trolling Apple by going to physically Apple stores and then visiting this website with the free to use devices there. And so basically these devices in show at Apple stores will be jailbroken pretty easily. Okay, so they did not like it. So the current status, again, I'm not into this community, so I'm not a super expert, but the current status is that there is a big community of people that pretend jailbreaks. What does it mean? It means that you have a bunch of people that are not technically skilled at all, but they go after the security researchers that, these are the ones capable to actually create jailbreaks and to find exploits, to find bugs and to actually exploit the bugs. And these guys get super aggressive. So it's quite toxic community where we have these random people saying, oh, when is the jailbreak? When is the jailbreak? And I mean, it's very, very annoying. And these actually the good people that find these bugs and exploits got pissed and basically stopped releasing them. Apple will fix these jailbreaks anyways. These are based on bugs, and Apple knows the bug because jailbreak is released, and then it will fix the bug and so forth. So that's more or less the state. In terms of toxicity, there seems to be a lot of drama behind between different parts of the iOS security community, where basically I don't know if it's fueled by competition and security researchers try to prove that they were the first one to find something. Again, I'm not in this, I'm just an outsider observer, but I'm just trying my best to describe what my impression is about this community. But I'm not into it to really discuss why there is this toxicity and so forth. I just know the outside, they seem to compete kind of thing. Okay, maybe there is some kind of inner drama that I'm not aware of. Okay, so in more recent news, last year there was this checkmate bootrom exploit. It was fantastic. This was unpatchable. I think I mentioned this news when we discussed about the secure boot, and these people actually find a bug in the boot ROM. ROM stands for read-only memory, and there is nothing much that Apple can do. So this basically allowed people with the Apple device with the vulnerable version of boot ROM to have a jailbreak that Apple cannot really fix. So Apple can release as many patches as it wants, but it's not going to be able to fix this bug. This boot ROM bug did not affect the most recent versions of Apple. Actually, the way that this bug was found was through patch diffing. So this researcher found a way to dump the boot ROM of device X, and then he got a newer device Y, and then he found that this boot ROM was changed. And the change was actually to fix a bug. And so from this diffing the two versions, he understood the patch. From the patch understood, hey, there is a bug here. And then I think him and other people, they managed to actually write an exploit for it. And now you basically have an unpatchable jailbreak out there for these previous versions of Apple. Okay, but it was very powerful because if you have an old device, then you know that there is a bug like this, where if you put a USB cable, then you can run the attack, and you cannot do much about it. You cannot patch it. Then, based on this bug, then they developed this checkra jailbreak, and that's a link there if you're curious about it. And please note the difference between bug, exploit, and full jailbreak. One thing is the bug that some people find. One thing is the exploit, which is this piece of code that somehow uses the bug to gain some advantage. You can find a bug that is not security relevant. For some security relevant bugs, maybe it's extremely difficult to exploit it. So maybe some of them are not exploitable. Okay, so from bug to exploit sometimes is very, very complex. And once you have the exploit just gives you maybe some basic code execution primitive, but you cannot do much with it. And then that's where the full jailbreak kicks in, or basically some kind of more complex code based on this exploit that somehow allows you to do more stuff, like dump interesting memory, or install applications and so forth. Okay, cool. All right, so in terms of reversing iOS apps, how do people do? Again, I'm not an expert, so that's a very, very, you know, for many Android things, I could just say, oh, we don't have time. In this case, even with all the time that, you know, with all possible time, I don't think I will be able to go really in depth on this topic. Again, but the idea is the same. Basically, you run the app in a jailbroken device, you dump the memory after it's decrypted, and now you can analyze the app. You can basically, yeah, there is this tool to load the app and wait for, you know, set the breakpoint for when it's decrypted and dump it. Then you take the app and you analyze it. You can use IDA, Ghidra, whatever you want. Note that you have tools like Frida. I presented Frida in the context of Android security, but Frida is nice. Frida allows you to work also on iOS jailbroken devices. And actually, you know, you remember the Frida, you write your main code that you want to run in JavaScript. Why did they choose crazy JavaScript? One of the reasons is that they wanted to be compatible with many different devices and architectures. So somehow they just need to have the JavaScript engine, the V8 in this case, and then you need to run it in Android and iOS, but then the code that you run the JavaScript is the same for both Android and iOS, okay? So people also use Afrida in this context. And then you can use Cydia or other environments, let's say, to install things like OpenSSH, other tools, so that you can have debugging and development environment. On this reversing stuff, I have a fantastic reference at the end of the slides. There is a pointer to, again, this resources from this Ivan that helped me out with the slides. So check it out. There is a link at the end. All right. So for the last part of this presentation, I wanted to go back in time to briefly discuss how things were in the past, so that you get an idea about how much the ecosystem evolved in terms of security. Okay. Again, some of the things I'm going to present now are going to be like, what is this, and so forth. Okay. So there was a crazy evolution in, from the very beginning up to now. So security is getting better after all. So again, modern devices are very secure, but let's say how it started. So iOS 1 was the first smartphone ever. And the question is, how secure was it? So it was an OMG level of security. There was no privilege separation, and all processes run as root. And, I guess if you just started a security class, you know this is a bad idea, okay? But then that was it. There was no code signing enforcement. So you could run, if you could get code execution, then you could run whatever you want. Again, remember, there were no third-party apps. But if you can get access to something, then you would have code execution. There is nobody checking signature, and you run as root. Thing is that if you find a bug, usually you have protection mechanisms, but even the security mechanisms that today we give for granted are not there, or were not there. There was no data execution prevention, no SLR, no sandboxing whatsoever. Okay, once you have a buffer overflow, bam, it's actually quite easy to get root. The crazy point also is that it was embedding libraries with known vulnerabilities. Okay, so were old versions of libraries, and people knew about bugs about these old versions, and these old versions were the ones in iOS. And I guess at the point there were no very sophisticated update mechanisms. So, again, this is less terrifying as it would be if you could install third-party apps at that point. At the point you couldn't do it. So it's not that you go on the Play Store and you install an app and now this app is root. You couldn't install anything. So to abuse this system, you would actually need to abuse a vulnerability, which apparently were there. And you didn't even need to create or find your own zero-day to exploit these things. And again, one of the most famous early examples is the libtif exploit, where basically, there was a bug in this libtif file format library. And the idea is that you get a malicious link and then you get root. Okay, so you click on the link and the attacker is root. In the context of jailbreak, this kind of a malicious link root, the user knows what it's doing, and that's the case I presented before. So you go to the link and then you get, you can install the Cydia and other things. In this case, of course, the threat model is different. It's not the user knowing what it's doing. It's more the user is strict to go to a link, and then the attacker somehow gets a shell with root permission. Another, threat vector at that point was SMS exploit, which affected iOS 2. At iOS 2, there was data execution prevention and sandboxing, but not ASLR. But unfortunately, the SMS component was running as root. So there was sandboxing, but it didn't affect all the apps. And the SMS component was actually running as root. So if you exploit SMS component, then you get root. Too bad, as you should, know at this point, the SMS code is actually quite important because it's, in terms of attack surface, it's attackable by a remote attacker. Okay, so it's pretty bad. Turns out there was a bug and remote root was achieved. I can send you an SMS and then I will get root. And remember, at that point, there was no way to disable SMS functionality. So you literally would get the phone, and if somebody knows your PIN, your telephone number, you will get root. This stuff is insane. And of course, it's crazy to even think this would be possible, in 2020. So in 2020, something like this would likely not happen. If it happens, it will be on all the news, and maybe there will be some super critical patch out there. We got very close with the stage fright bugs in 2015, but so it's not that it's impossible, but having remote root, and maybe there was not even ASLR. That's when stage fright bug was found, at least in the latest version of Android. At that point, ASLR was already there. But is not as bad as this case. Okay, so that's just to give you an idea how much progress we did as a security standpoint for these mobile devices. And one other fun example was the iKey worm. Basically, people were jailbreaking iOS 2 to install custom apps, and these people were also installing SSH servers, which was running a root, of course, not sandboxed. So if there is let's say a bug there, then you will get root remotely. But maybe SSH servers don't have bugs, or it's very difficult to find bugs there. Well, these people were installing these servers with default username and password. So you did not need a bug in a SSH server. You can just use default username and password. Many people were not changing it, and so you basically have a wormable bug out there. So you have worm. In security, worm is a malware that can spread itself, attacking other computers around. And again, this was a wormable bug. There were several, use cases for this bug, for this worm. And some people were just, some instances of the worm were just recrawling victims. If you don't know about recrawling, check it out. It's a usual prank, or basically you get redirected without you expecting it to. It's a very interesting video. They would log phone for ransom, stealing content, and botnet. I have a demonstration here. This is a very important demo, so please check it out. I'm telling you, I'm going to ask for this at the final, so check it out, please, just to get an idea about how these attacks would actually work, okay? And how the user would feel after it will get attacked. Okay, so that's the last slide. Again, I have some pointers. These are resources that I consulted to prepare these slides. This last link is the link I mentioned before. It's some kind of a GitHub repo with many information about how to get started in reversing iOS apps, and that's how I actually met on Twitter Ivan. That was so kind to to triple check my slides to make sure I didn't write anything stupid. I probably balance it out with saying something stupid, but for the 10 people other than my students that are going to watch this video, let's keep this a secret. Don't tell him. Okay. So with that being said, we are done for this iOS stuff, and please, I have another video coming up with kind of a final big recap. There is important information there. It's not just a summary. So it's going to be about a look at the future. What if you want to start with this security research field? What are the things you need to know about how this publication system work, and so forth. So please do not treat this last video as just a summary. there are important information, and I would really appreciate if you would check it out. Okay. All right. Thanks for sticking around. And as always, let me know if you have questions. Ciao, ciao.